Okay, so this is going to be a supplemental video. This is one that kind of introduces calculus in terms of physics. So what we're going to take a look at is just some of the basics. This is mostly intended for my APC class, one that is actually a calc-based physics, but this is broadly for anyone who's interested in the calculus applications of physics. Now, I've got a few notes that I want to go through. There'll be a couple different parts to this, but first thing that we want to talk about is, well, I'll go ahead and introduce the two main types of calculus. We have differential, which deals with derivatives. That's usually where most calc classes start, and that's what we're primarily going to look at. But then the other type is integral. Integral, words are hard. And then that one is, wait for it, integrals. Described as integration. Basically, they describe two different relationships. Differentials, derivatives, will tell you a bit about rates of change, whereas integrals will actually add up changing effects and see what they're doing collectively. That's the way to think about them, and we're going to take a look at that and try and give you a rundown on that. Now, for many of the calc classes, you're going to start off, especially in the classically mathematic way, where you're looking at things like limits. You'll study the limit of a function as x goes to 0. We're going to talk very briefly about that, but for the most part, I found it useful afterwards. When I first learned it, I was totally confused by it, and I didn't really understand why it was useful. It was much later when I started working with calculus with physics that I started to understand what I was doing with calculus, and that's when I looked back and thought, oh, that's what the limit stuff is about. My goal right now is to hopefully give you that kind of conclusion without having you to necessarily go through it for yourself. We're going to start off looking at differential, but for calculus-based physics, it turns out we're going to be using both of these. I'm going to be shooting two videos. This one's the first one in which we kind of introduce the ideas of calculus and get across the basic function of how you work with it. And then the second one is going to be starting to apply it right away in some of the first material we go into, which is kinematics. Let's talk about what a derivative is. So I want you to imagine that we've got a graph. We've got some y value here on our vertical axis, and we have some x value here on our horizontal axis. Now, if you're in class with me by now, you probably should have seen already that it's not always y that's over here, it's not always x that's over here. In kinematics, we would have position and time, for instance. That would be a great one to look at. Or we might have force versus acceleration. All these different graphs represent different things in real life when you're dealing with physics. We're going to look at this strictly from kind of a math viewpoint to get the ball rolling, and then I'm going to show you some of the notation so that later when you're seeing it in a physics application, you can fill these in with whatever they are. The main reason I bring that up is a lot of times in calculus, you'll always deal with y and x. I want right off the bat to let you know that they're just placeholders for things that we're actually going to be working with in real life. They're variables. But when you get to physics, those variables mean something. They're not just letters on the page. Let's take a look at a graph. Let's say that I've got something along the lines of something like this. It has a vaguely parabolic shape. Now, just because it's curved like that, don't assume it's a parabola, because A, I drew it by hand, so it probably isn't. And B, it could be x to the cube, or x cubed, it could be x to the fourth. There are a lot of things that may end up with a curved shape like this. They're not always parabolas, so be careful assuming they are. But let's just go with what we've got here. Now, the big thing that we're interested in when it comes to differential calculus is something called slope. Now, hopefully most of you have encountered this before. It's one of the first things that you do with graphing, and if you have a straight line, you can have y and x. Slope basically tells you how steep this thing is, and you would find the slope by doing, you could take 2 points on your line, and we can do rise over run. Now, whichever of my physics classes you're in, by about a month into class, this is something that you'll have dealt with because we do it pretty early with kinematics, graphical kinematics. Rise over run. That would be the same thing as, let's say that this is y2, and this is y1, this is x2, and this is x1. So we'd have y2 minus y1 over x2 minus x1. In short, that's kind of the slope. what a slope is actually doing is telling you the key part of what differential calculus is actually about. Rate of change. In short, I want you to imagine a couple different lines. Let's say I'll do one in blue here, and I'll do one in red up here. Okay? What we're looking for when we do rate of change, if we have y over x, and we're looking at the rate of change, basically you're saying this. If I change x by just a little bit, go from here to here, what does that do to y? Okay, well, if I'm looking at, say, the green one here, if I go from this x to that x, then I go from this y to that y. I have an x change of about this, and I have a y change of about this. Okay, that's what the rise over run is. I have this much of a change in y over this much of a change in x. The blue one, I have this much change in x. If I were to take, say, these 2 points, all the same x's, I have this much of a change in x, but I end up with a really tiny change in y. I have a small number up here and a big number on bottom. This, my slope, becomes a small number. What we're actually describing is if I change x by a certain amount, what does y do? For the blue line, I change x by a certain amount, y barely changes. For the green line, I change x by a certain amount, y changes a decent amount. Pretty comparable. And if I change, let's take a look at the red. If I change x from here to over here, about the same as this, I end up with a y that goes even bigger than my hand will actually go. I end up with a big number over a small number. I end up with a big slope. It's very easy to lose track of this when you're actually studying this in math because it's just, well, slope, lines have slopes, let's find it. But the first thing that we need to understand is what a slope is actually telling us. It's telling us how things are changing. Now, to tie this to some of the kinematics that you may or may not have seen, we've got things where we describe velocity or speed. How fast you're moving is how quickly you are changing your position. If in 1 second I move really far, then I'm moving fast. I have a high speed, a high velocity. If in 1 second I barely move at all, I'm moving very slowly. Physics is about rates of change. In fact, one of the first people to actually propose this type of mathematical approach was Isaac Newton, and his entire reason for doing it was to find out about rates of change. Now, it's easy to get lost on this when you're staring at the graphs or equations, but it's helpful to keep track of that. Let's take a look at this. If I were to go through and find the rate of change for this function, I don't even know what this function is. I could try and claim that it's a parabola, but this is just what I've got drawn, which is perfectly fine. I can do the following. Well, if I go from an x from, let's say here, we'll call this x1 to x2, I could end up with the following. We'll end up with here, here. And I end up with a change here of y1 and y2. So I change by this much, it changes by this much. Here's the problem with this. Now, if you're dealing with a straight line, it doesn't matter if I do this and then this, or come over here and do that. You'll see with the green line, no matter how much, as long as I move this much in x, I'll end up moving this much in y. Still matches up. That's with a straight line. We have a constant slope. That's basically what defines a line. When you start getting something that isn't a line, we run into a problem. Because look, if I go this far in the x, I go this far in the y. But if I come over here and go this far in the x, I've gone this far in the x. Used to be like this. I've gone this far in the x. I'm no longer going the right distance in the y. And as I go further out here, I'm going to go off of the page. In short, if you're not dealing with a line, you don't have a constant slope. And the slope describes how this thing is changing. Down here, we have a very low slope. If I change my x a lot, I get a small change in y. Over here, if I change my x a lot, I get a decent change in y. And over here, if I change my x a lot, I get a huge change in y. In short, my rate of change here is constantly changing. The rate of change is also changing. So we could also look at the rate of change of the rate of change. As crazy as that sounds, that's basically what calculus does. We are looking at trying to describe how quickly things are changing, because that relates to real life. If we understand how things are changing, we can predict what they're going to do next. Let's take a closer look at this and see if we can understand what's going on with a derivative. Now, we're trying to find a slope. Now, the thing about this is I could find a slope here between these 2 points, or I could find a slope here between these 2 points, or I could find a slope between these 2 points, or I could find a slope between these 2 points. The problem with a non-constant slope is, depending on what area I'm looking at, I'm going to end up with different values. What we're looking at here is the average rate of change between this point and this point. Sometimes we're less, so here's my average slope. Sometimes we're less, it's changing much more slowly, and sometimes we're more, it's changing much more quickly. What calculus is about is saying, okay, let's move beyond the average. What I want is to be able to find out what the slope is at any given point right here. The idea behind this is the following. So if I want to find, let me redraw this real quick so I can clean this up some. Let's go back to kind of the same shape that we're working with. I've got a curve here. We've got x, and then we've got y. All right. Let's say that I want to find the slope. I'm going to say at this point right here, because at every single point, I end up with a different slope. We're doing something called a tangent line, a line that just barely touches up against it. In fact, let me get something that might be a little bit better for this. Also wood. So I've got, if I'm looking at this point, I can put it right there, and I've got a line that goes along like the wood. This is a different tangent line. Basically, it touches at a point and will tell us what the slope is at that one point. That's the idea behind a tangent line. Let's see, I want to find out the slope at this given point. Now I want you to think about the following. We normally find a slope by rise over run. So what I could do is I could start off by saying, okay, what if I take the slope between these 2 points? I could draw a straight line here, and I could do the slope. Although the slope of this is not necessarily going to be the same slope as that. In fact, this might be entirely off. Well, I could get a lot better if I come in and I squeeze these in a little bit more. Instead of having the points way out here, what if I bring them in a little bit closer? That's starting to get much nicer. Okay, well, I'm getting a better result, getting closer to my slope as I bring these little points in. So what I'm going to do is I'm going to start getting them really close. That's going to get me very, very close to what my slope is. So if I'm far out, I may not necessarily get a good slope. Especially, let me try this on one other thing. Because if that is a parabola, you may be thinking, those all look pretty similar. Let me show you something that gets the point across a little bit better. This is a function. Could be a real life function. Let's say that I want the slope right here at this point. I could start off, like I said, by going from here to here. Well, that's going to get me a terrible slope because that's pointed up like this. But if we imagine the tangent line here, it's actually down. So that's a terrible approximation. But what I'm saying is we can get closer if we start bringing these points closer together. I get something like this and this. That's getting me much closer. This and this. That's getting me much closer. I apologize, my board's a little bit out of alignment. What I want you to imagine is this. Any point on here, because this one is up like that. This one's down like that. This one's also down like that, up. I could go around with my board, and I could do, okay, so here's the slope on that. It's going around, goes back down like that, and back up. Hard to do this with the projection. Back over here, goes around like that. Basically, my slope is always changing. If I do a very wide value, I end up with a terrible value for my slope. It doesn't match this at all. But as I bring these points closer together, so you can imagine that this is my x2 minus x1 over y2 minus y1. I can get this more accurate, much closer to the actual slope if instead I shrink this down to x2 and x1. And this one becomes y2 and y1. Or I can shrink it down even more. My x, x2, x1. My y, y2, y1. I want you to notice this. To get a better representation of what the slope is right at that point, how the thing is changing, its rate of change at that point, is to shrink down the space you're looking at. We have a terrible response for this graph if we look at a large x1, x2. But as we start shrinking these points in, we get them closer and closer, we start getting a better result for exactly what we're looking for. So I want you to think about this. How would we make this the most accurate and get the slope right at that point? What would we do? We keep getting better and better if we shrink this down. Well, we want to shrink this down until it can't get any smaller. This is where that limit stuff comes in. Because they ask you, find the limit as x goes to 0. Well, for me, and I may not be remembering this perfectly, but what I took away from that afterwards when I look back and I realized that this is what calculus is doing, we are shrinking these intervals down to make them infinitely small. We're taking the limit as delta x, x2 minus x1, goes to 0. In other words, we're getting these so close together that they're pretty much right on top of each other. Don't think about that too much because it'll hurt your brain. But I want you to imagine that we're shrinking this down, the smallest thing you can possibly imagine, and we're making this even smaller. And in doing so, we get our points right here. And whatever we get when we do this, the green dot for y2 minus y1 over x2 minus x1, will actually be equal to the slope at that point. But only if y2 and y1 get infinitely close to each other. How we would normally describe this, as we've mentioned before, is we could say that the slope is equal to delta x over, or I'm sorry, delta y, bad Sanchez, delta y over delta x. Now, we've talked about this in class. Delta means specifically final minus initial. Well, what we're doing is we're no longer dealing with a finite y2 minus y1 or x2 minus x1. We're shrinking it down to be as small as it possibly can be. We have a special notation to denote that. Instead of being a delta y, an actual physical displacement, they're so close together that instead we mark it as dy dx. D is representing kind of the similar thing as delta, but it's letting you know that we're not dealing with an actual distance between the two of them. We're dealing with 2 points that are so close together that for all intents and purposes, they're the same point. The only difference between that is basically our imagination. Give me just a moment. Okay, just had to check the camera. So, this is one of the main things that I'll actually bring up in my class, why this notation even exists and what D actually represents. What D represents is it means that we're dealing with an infinitely small piece of x. Instead of having a delta x, x2 minus x1, and a delta y, y2 minus y1, when we take the derivative, when we want the rate of change, the slope, at that one spot and that spot only, we shrink these down to where they are no longer a finite delta y, a space here and a space here, where there's a finite distance between them. We shrink them so close together that the only reason that they're not 1 point is because we say they're not 1 point. It's the smallest thing you can possibly imagine, and then cut that in half. That's what this notation means. It's no longer a finite delta x, we have a dx, infinitely thin piece of x. Instead of one line here, we've got a point. dy, instead of a delta y, we've shrunk it down to an infinitely thin piece of y, dy. When you see these notations in calculus, d followed by the variable is telling you that you are dealing with an infinitely small piece of x and an infinitely small piece of y. And the reason we're doing that is because that's what will get us the slope at this point. We're shrinking this displacement, if you will, or the difference here, down to 0, or very close to 0. Hence, the limit as something approaches 0. We're going to get as close to 0 as we possibly can. It'll be the little brother in the car ride of mathematics. You know, the classic, I'm not touching you, I'm not touching you, I'm not touching you. They'll get as close as they possibly can. They won't actually touch you because then things get bad. All right. This is a bit of background on what the idea behind all of this is. What a derivative is actually doing. When you take a derivative, and we're going to look at the mechanical side of this, of physically how to do that with mathematics, but I want you to understand ideally what we're actually working with and why the notation is what the notation is. We get an accurate representation of the slope at exactly this point by shrinking our interval down until that interval is right on that point. And as you do that, your slope will become the slope at that point, the slope of the tangent line. All right, that's a bit of derivatives. Let's take a look at what the opposite is. It's called an integral. And what the integral does is it adds up a bunch of infinitely small pieces of things. Okay, well, so let's take a look here. I'm going to set back up a very similar one to what we had just a moment ago. I'm going to use my crazy town banana pants function. Something like that. Now, if you've gone through this part in my class, you'll already know that graphical kinematics, one of the things that we look for is the slope, and that allows us to tell things like to go from position, where I'm at, to velocity, how quickly I'm changing my position. Slopes give you, wait for it, rate of change. The other thing that you can take a look at in graphical kinematics is the area under the curve. Derivatives deal with the slopes, and integrals deal with the area under the curve. They're two different parts of kind of the same thing. What we do mathematically with derivatives tells us about the rate of change of whatever we're looking at. Integrals will actually move us back the other way. So if we find the derivative of my position as a function of time, I'll end up with my velocity. I can go from my velocity by taking the integral with respect to time, and it will bring me back, I'm going to derivatives, it will bring me back to my first stop, which is position. Take a look at one of my other videos to take a look at that. In short, this is the other part of calculus, integration. Now, this is probably going to be very premature for many of you, but we could do the following. We end up with a way of writing this would be y equals the integral of, or I'm sorry, pardon me. I'm used to thinking about this in terms of my actual, give me just a moment. I'm going to change this up just a little bit. I'm going to fictitiously make up that this is a force and that this is a displacement or a position, delta x. Now the reason that I'm doing that is I'm actually going to use one of our full physics equations, which is the work done is equal to the integral of f dot dx. Now, for those of you who are not dealing with the calculus side, I usually introduce the work equation as force times delta x times cosine of the angle between them, but that only applies when you have a constant force. In this case, we can imagine that this is my actual force. What I'm trying to find is the work, which is the integral of this, which means I'm going to try and find the area under this curve. One of the first things that you learn is the following, and it's basically an approximation. What I can do is, well, let's do an approximation here. I'm going to have it where I do this. I'm going to make a bunch of rectangles. And then I can find the area of the rectangles, add them together, and that'll be an approximation of my area under the curve. So what I can do, let's find this rectangle. Let's say that this is from 0 to x1, this is x2, and this is x3. And then we've got f1, f2, f3. If I'm going to find the area of this one, it would be, well, it's a rectangle, so I would do base times height. So I have x1 minus 0 times f1 minus 0. So that's going to be, let's see, my area here for the very first one is going to be x1 times F1. That's my area. The area of this one, so this is area 1, area 2. This one would be, well, x2 minus x1, x2 minus x1. That gets me my base. And my height is f2 minus 0, so we'll call that f2. And then area 3 is going to be x3 minus x2. That's my base. And my height is f3. And what I'm trying to do is I'm trying to find the area under the entire curve. Now the problem, and many of you may already be screaming this is a terrible way to go about this. I've got all of this empty space here that I'm not filling in at all. I mean, this is giving me an approximation, but a terrible one, because I've got so much empty space. What I'm trying to do is find all of the area under the curve here in between my graph and the x-axis. This is an approximation, but it's a bad one. It's a very bad one. Okay, how can I make this approximation better? Well, I could instead do the following. I could make this one, and then this one, and then this one. I can make smaller rectangles. And I can find, let's say the base of each of these is 1. So I have a thickness of 1 here. I have a base of 1, 1, 1, 1, 1, 1, 1. And then I can find the height. Here's the height of this one, and the height of this one, and the height of this one. And I can multiply those together, and I can add them all up. But once again, I'm missing parts in here. But this is way better than the one that I did just a moment ago. Let's say that this was a width of like 8, 8, 8, not drawn to scale. I got a much better approximation of it by, instead of having a wide base, I can get these thinner and thinner. In fact, one of the nice things that I could do is, what if I make them really, really thin? I'm going to get really, really close, but I'm still going to have little gaps in there. How can I get the full thing? Well, okay, I want you to take a look at this real quick, what I've got set up here. I would have the value of the function here, f2, times the interval that it's over, x2 minus x1. That's what we're dealing with each of these. With the red ones, I would have the value of the function here times its interval, okay? So, and then I would add all of those up. So I need plus, plus, come on board, plus, plus. And then my total area would be those added together. How I can get this in an actually correct full area under the curve is the following. And some of you may be thinking about this already. Remember what we did with the derivatives? To make it more accurate, I shrunk things down. I make this more accurate by shrinking down the width of the rectangles that I'm dealing with. What if I make them these rectangles infinitely thin? It's basically a line. It would be a line that goes up and touches every single point along here and fills everything in. We would end up with our actual area under the curve. Well, for that, what I would need is, let's say f1, f2, f3, f4, f5, f6. Basically, what I'd end up with is the following. I would find my area under the curve, which would be equal to, well, the first area, let's see, and that would be the height, let's call that f1, times the base. I've got the height of the rectangle times the base, but remember, my goal was to make that infinitely thin. Well, it would be an infinitely small piece of x. How do we denote infinitely small pieces? Dx plus f2 dx plus f3 dx plus etc., etc. What I mean by f1 is the very first one comes up to this height, that's f1. Then I nudge over an infinitely small piece, and then the next one's f2, then f3, then f4, then f5, f6, f7, f8. Now you may be thinking, okay, that sounds great, Sanchez, but now I have an infinite number of lines to add together. That's what an integral is. I want you to look very closely at this. We have f, the value of the function at one point here. This would be my equivalent of y. But it's whatever that value is times the infinitely thin piece of it. That is the area of my infinitely thin rectangle, and I'm going to add it to the next one, and the next one, and the next one. Well, instead of writing out an infinite number of terms, in fact, I should put dot, 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 because that goes on for forever. I end up with an infinite number of them. Okay, well, instead of writing it that way, because that would take us forever, we have a different notation. My area under the curve would be equal to, we use this squiggle, because it looks like an S for summation. Summation means to add everything up. I'm not going to do F1 or F2 or F3, I'm going to do F, and it's technically a function of X. Because whatever my X is, let's say X equals 3, well, I'll end up with an F up here somewhere. So I've got F is my height, whatever the value of the function is. It could be F1, F2, F3, F4, whatever, times the thickness of that rectangle. This summation symbol means that I'm taking each of these and I'm adding them up. This is where you get the notation for an integral. And one of the things that I love to bring up in class is you can't have this. This means absolutely nothing. The dx has to be there because it's the thickness of your infinitely thin rectangles. You're not actually having an area that you're multiplying or adding together, I should say, an area that you're adding together. You have nothing to multiply this with. That's just a height. You have to have that infinitely thin piece of x. Now, I apologize about setting this up. The work is something that we deal with in physics. It's a real thing that means something and is a quantifiable value and is very, very useful for solving complex problems. And we can find it by doing the integral of our force, which is a function of our position. Now, if your force is constant, then the constant comes out of the integral, and then it just evaluates to delta x. So that's the simplistic case. But that's me putting it in terms where I could set it up and know that I was getting across what I wanted to. The key on this is, for the integral side, that we end up with dx. Why is it there? Because what we're doing is to fill in the entire area, we're shrinking these rectangles down to smaller and smaller until their thickness is not x3 minus x2, but it is infinitely thin dx. All right. Little bit of final stuff on this for dealing with calculus. Give me just a moment while I get that set up.